And with that, let me introduce our first speaker. Our first speaker is Professor Jack Lunsford from Texas A&M. I'm very sure many of you know him. He has been working in the area of surface science and catalysis for the last 25 years. He's extremely well recognized for it. He's a winner of Paul Emmett Award in Fundamental Catalysis. He also has won the Catalysis Society of Metropolitan New York Award for Excellence in Catalysis, among a number of other awards. I'm going to keep this short. And he is also on the editorial board, or has been on the editorial board of Journal of Catalysis and Zeolites, and has been a Guggenheim Fellow. And it's really my pleasure, great pleasure, to give you Dr. Lunsford.
Well, I'm honored to receive the Langmuir Lecture, and I appreciate your attendance at the lecture this evening. What I would like to do today is to give you an overview of some work which we've been carrying out over the last decade or so, looking at the problem of surface-generated gas phase radicals. That is, primarily organic radicals that are formed on a catalytic surface, primarily a metal oxide. Then these radicals go into the gas phase, where they can be studied by a variety of different techniques. As I began to think about this, I recalled some early work that Langmuir himself had done, so I think that it's somewhat fitting that my work parallels some of the early work that Langmuir published. And if we have the first slide, I suppose I have some control up here. Failed to see the little, is there a controller here? Oh. Okay. This is a rather lengthy quotation, but in the period of about 1911 to 1914, Langmuir was looking at the formation of methyl radicals, hydrogen atoms from hydrogen molecules. And these atoms were believed to be formed either in the very high temperature region around the wire in the light bulb, or actually, as indicated in this quotation, they were formed from hydrogen which diffused out of the tungsten wire and then traversed across the light bulb from one side to the other. I think it's interesting to go through this. It says, thus over the range of temperature, and here he's talking the temperatures of about 1500 Kelvin, and at pressures in which the cleanup of hydrogen is observed. In this particular case, he was really following the disappearance of hydrogen. The degree of dissociation of hydrogen is quite appreciable. This would indicate that a part of the hydrogen which diffuses out of the metal is in the form of atoms, even after leaving the metal surface. At ordinary pressures, these atoms would combine in pairs to form hydrogen molecules, but at the pressures with which we are here dealing, this normal free path of the molecules is several times the diameter of the lamp bulb, and hence the atoms fly directly from the surface of the wire to the surface of the glass without having any opportunity to combine. And some of these atoms of hydrogen are held on the surface of the glass by adsorption. So as far as I'm aware, this is the first example of atoms being formed from molecules and surfaces, and then these atoms being emitted into the gas phase where they can enter into subsequent reactions. Now, since the time of, let's see, I'm going to need a little help on advancing these slides. All right. That might be the best. Okay, thank you.
Okay.
Yes, ready. Since this early work of Langmuir, a number of spectroscopic and spectrometric techniques, mass spectrometry, have been used to study these radicals which emanate from surfaces of catalytic interest. And I've listed 6 of these here, one of which is mass spectrometry. Matrix isolation infrared spectroscopy can be used. laser-induced fluorescence spectroscopy and its cousin resonance-enhanced multiphoton ionization techniques have been used. Photoelectron spectroscopy has been used, and finally, the technique that has been our choice has been that of what we call matrix isolation electron spin resonance spectroscopy. And we'll go to the next slide, please. Our work in this area was really motivated by a long-standing interest in heterogeneous catalysis of what is so-called heterogeneous homogeneous reactions. That is, reactions which are initiated on a surface, which proceed in the gas phase and are essentially completed in the gas phase. In other words, intermediates are formed on the surface, but these intermediates, be they radicals or not, enter the gas phase where the subsequent steps in the reaction take place. And I was particularly motivated by some work which George Kelks and his co-workers carried out at the University of Wisconsin at Milwaukee, in which they were looking at propylene partial oxidation to acrolein, and primarily as a result of modifying the reactor design and having post-catalytic volumes and so forth. Kelks and co-workers concluded that an allyl radical was formed on the surface of bismuth molybdate catalyst, and this radical could either further react on the surface by losing another hydrogen and picking up an oxygen to forming acrolein, which would be the so-called straight heterogeneous approach, or that the radical or some reactive species that entered the gas phase undergo subsequent reactions and form products which, such as propylene oxide, which would not typically be expected to be formed on the surface. So here we have an example then of a heterogeneous, homogeneous reaction pathway, and we were interested in our laboratory seeing if we could build a system where we could examine these allyl radicals as they came off the surface of bismuth molybdate. And the next slide, please. The system which we have developed and has proven to be very reliable and has given rise to a number of different experiments is essentially what we call a MISR system, a matrix isolation electron spin resonance system. We have a hot catalyst bed here, which typically is temperatures between, say, 400 degrees C all the way up to around 800 degrees C. Over which we pass the hydrocarbon from which we expect to make the radicals, molecular oxygen or some other oxidant, and argon, which is the gas from which we form the matrix. The radicals then leave the surface, enter the leak, and at this region initially we operated about 1 bar. We've since been able to go up to 1 atmosphere. The pressure on the other side of the leak is on the order of 10 to the minus 5th bar. So radicals entering the leak then more or less have a free path to traverse and be collected on a cold sapphire rod, which is at about 15 Kelvin. And after collecting the matrix for a period of about 20 to 25 minutes, the rod is then lowered into an ESR spectrometer, or a microwave cavity of an ESR spectrometer, and we look to see whether indeed we form the radicals, and if so, of what type. Next slide, please. And the first study, as I indicated, was that of looking for allyl radicals over catalysts such as bismuth molybdate. And I show you in spectrum A the very characteristic spectrum of the allyl radical formed from propylene, in this case over bismuth oxide. And if excess oxygen is present in the system, we form the allyl peroxy radical, which also has a characteristic ESR spectrum associated with it. Now, in the case of the bismuth molybdate, we found that the numbers of radicals formed in the gas phase were relatively small. But when we look at bismuth oxide, we found that quite appreciable numbers of radicals were formed and entered the gas phase. And have the next slide, please. And so we picture a reaction such as this occurring, that the propylene attacks the surface or is adsorbed on the surface interacts with an oxygen, which is part of the bismuth oxide. Hydrogen is subtracted. We make the allyl radical, and then the allyl radical enters the gas phase, and provided that there's no excess oxygen there, we will be able to collect it. Now, when we began to look at the stable products that are formed, we found that over bismuth oxide, the primary stable product is 1,5-hexadiene. And 1,5-hexadiene is just the stable product that would result from the coupling of two allyl radicals. On the other hand, over bismuth molybdate, which gave relatively few allyl radicals, the primary product was acroleum. And presumably what happens on the bismuth molybdate is that the radical is stabilized on the surface, and before it can desarb and be collected, it undergoes, again, the loss of a hydrogen, the gain of an oxygen to form acroleum. So surfaces are quite different with respect to their ability both to generate the radicals and to actually release the radicals in the gas phase. And we'll be having more to say about that later in the talk. We'll go to the next slide, please. Now, we were interested in doing a rather broad survey to see if we could determine the factors both with respect to the type of metal oxides and the other factors with respect to the nature of the molecule itself that gave rise to the formation of these gas phase radicals. And so we examined a series of metal oxides and a series of simple organics all the way from propylene to ethylene. And these particular molecules, you'll note, have different CH bond strengths for the weakest CH bond in the molecule. And one of the things we were interested in seeing is whether the CH bond strength affected the ability to generate the gas phase radicals. Now, for purposes of this discussion, let's focus on two catalysts, bismuth oxide and lithium-promoted magnesium oxide. I'll tell you why we were interested in lithium-promoted magnesium oxide in a moment, but let's just say that it's a very good radical generator. And so let's look at two catalysts and compare two reagents. The allyl radical, or excuse me, propylene, which has a relatively weak allylic CH bond, only 89 kilocalories per mole, and methane, which has a much higher CH bond strength of about 104 kilocalories per mole. And you can see immediately that bismuth oxide and lithium mag oxide are able to generate allyl radicals rather well from propylene. But when we turn to methane, bismuth oxide has a very difficult time in attacking the methane and generating the methyl radical, whereas the lithium-promoted mag oxide is very effective in generating the methyl radicals. And what we suggest, and again I'll amplify this a little bit more in a minute, that there are specific types of oxygen on certain of these metal oxides which are very effective in abstracting hydrogen atoms. And this particular form of oxygen exists with the lithium mag oxide. But on a material like bismuth oxide, these specific and very reactive form of oxygen do not exist, and therefore they cannot attack a strong CH bond, but they can attack a weak CH bond. Now, is bond strength the overriding story? I think the answer is no, that one must consider other factors in determining whether the radicals are formed. And if we go on to the next slide, please. We next then focused on one particular oxide, namely the bismuth oxide, and we looked at a series of fairly comparable molecules, but molecules which had different allylic CH bond strengths. And we looked at 1-butene, propylene, and isobutylene. And I show you one spectrum, that is the 2-methyl allyl radical, which is formed from the isobutylene. And the upper spectrum is that of the experimental spectrum, and the lower is that which has been simulated based upon the coupling constants and the G value. But more interest is the results shown in the next slide, in which we now have ordered the molecules according to increasing weak CH bonds. Butene having a CH bond strength of 83, the isobutylene 86, and propylene 89. And we see that the total number of radicals do not follow this progression of bond strength at all. So there's something more than just bond strength that needs to be considered. And one of the factors that I think would be obvious as you simply look at these molecules is that they have differing numbers of allylic CH bonds. For example, here we have 6, and here we have 3, and here we have 2. So simply the number of allylic CH bonds more or less predicts the numbers of radicals as long as the bond strengths are more or less the same ballpark. Of course, if we go to very great differences in CH bond strength, as in, for example, ethane and methane, then the CH bond strength is going to play the dominant role. But as long as the CH bond strengths don't differ by that much, then other factors, such as the number of weak CH bonds, become more important. Well, I would like to turn at this point to the next slide. Another area of interest, which has been that of trying to understand the origin and both the mechanism and the nature of catalytic properties for catalysts which are able to activate methane and promote the oxidative coupling reaction. That is, to take methane to ethane and ethylene. And I mentioned before that we had looked at magnesium oxide, and in fact lithium magoxide turns out to be a relatively good catalyst, both with respect to activity and also with respect to selectivity in converting methane to ethane and ethylene. And so it was of interest to us then to try to understand how the methane was activated and the possible role of these surface-induced gas phase methyl radicals. And to put things in a historical perspective, I need to turn it around and tell you that first of all, we were looking at the formation of the methyl radicals, and then that led us to the discovery of the lithium magoxide catalyst. So the fundamental work, the initial work, was really done on the generation of these gas phase radicals. And we'll go to the next slide, please. Again, the methyl radicals have a very characteristic 4-line spectrum, so there's no problem in observing them. And if excess oxygen is present in the system, again, we form the peroxy radical, in this case, the methyl peroxy radical. Go to the next slide, please. We early on found that lithium increased considerably the ability of magnesium oxide to generate these methyl radicals. This is the concentration of methyl radicals that are observed on pure magnesium oxide. As we began to introduce more and more lithium, and now this is lithium ions, this is lithium carbonate, the numbers of radicals increases by about an order of magnitude. Likewise, the center which we propose as being responsible for the generation of these radicals also increases. Next slide, please. Now, we have done a number of qualitative experiments to show that the ability of a particular catalyst to generate the radicals correlates with the general overall catalytic properties. And this is just one such correlation where we have looked at sodium-doped calcium oxide, looked at the relative C2 yield to the 1/2 power because it's a bimolecular reaction, and compared that with the relative radical production. And you see that there is good agreement between our ability to generate the methyl radicals and the C2 yield as determined in a conventional catalytic reaction. And go to the next slide, please. Well, the qualitative relationships are nice and provide us some information, but one could always ask the question, are you just seeing a relationship, a proportionality between what appears in the gas phase and what really occurs on the surface? Are you really generating enough radicals in the gas phase to account for the C2 products that are being observed. And to answer this question, we have looked at the system operating at atmospheric pressure, and one in which we have moved our probe at progressively greater distances away from the catalyst surface, from the exit of the catalyst bed, and have observed the decrease in the rate of, in the concentration of radicals present as a function of distance from the catalyst bed. Now, knowing the flow rate, we can convert that distance to time, and if we plot 1 over the radical concentration versus the time, then we should get a straight line, since it's a simple bimolecular reaction, whose slope is the gas phase rate constant, whose intercept gives us the methyl radical concentration exiting the catalyst bed. Well, I won't go into details about the rate constant, but it is generally in good agreement with that which has been reported for the radical coupling reaction. Of more interest to us now is the concentration of methyl radicals. We have the next slide, please. And I'll just take you to the bottom line here, that the rate of radical production divided by the rate of C2 production from the methane times 100 gives us 40%. That means that 40% of the C2s which we observe in the particular system came about from the coupling of the gas phase methyl radicals. And I would place this as a lower limit, and I think the number is greater than the 40%. We have now done lanthanum oxide using a somewhat improved catalyst configuration, and have gotten this number up to something like 70%. We'll go to the next slide. Let's skip this one and go on to it. Now, more recently, we have become interested in still another aspect of the problem, and that is how do methyl radicals react with metal oxides? Because for the net production, one has not only to generate the radical on the surface, but the radical must be able to leave the surface, and at least for us to be able to detect it, to get out of the catalyst bed. But more importantly, from the catalytic standpoint, it must be able to survive long enough to couple before it reacts back with the metal oxide in a deleterious fashion to give carbon dioxide. So we have built a two-catalyst system, one in which we have a radical generator, and typically our radical generator is samarium oxide. And then we have another catalyst here, which is our methyl radical scavenger. And that could be either anything ranging from quartz chips all the way to lithium magnesium oxide. And what we are finding, and this is really some of our most recent work, is that there are tremendous differences in the ability of metal oxides to react with methyl radicals. Quartz chips, for example, are almost inert. The radicals just bounce right through them and appear on the other side and are collected. But certain other metal oxides react with or scavenge almost 100% of the radicals that impinge on them. And in the next slide, just to go through a brief comparison of the lanthanide oxides, we had previously shown that among the lanthanide oxides, as far as radical formation was concerned, there were very, very large differences in their ability to generate these gas phase radicals. For example, lanthanum oxide is very good, but cerium oxide is very poor. And neodymium oxide is good, and samarium oxide is good, and europium oxide is very poor, and so forth across. So there are very large differences in the ability to generate these gas phase radicals. And now, at least we know in part why that is true. It's because that certain of the oxides are also very good radical scavengers. For example, essentially 100% of the radicals that are formed elsewhere and impinge upon cerium oxide react ultimately to form carbon dioxide. So there's no real net production of the methyl radicals on cerium oxide. And the same appears to be true for all of these oxides which have variable oxidation states, meaning the cerium, praseodymium, and terbium oxides all have multiple oxidation states which we believe to be involved in the reaction with the methyl radicals. And I think that what is happening is that we form methoxide ions, and in the formation of methoxide ions, an electron is donated to the metal ion, and thereby reducing the metal ion. So you need to have a metal ion with two or more oxidation states. Go to the next slide, please. Another important observation that has been made in a number of different catalysts for the methane oxidation is that lithium or other alkali metals have a very significant effect in improving the selectivity. And I think we can perhaps see the origin of that, at least in part, by these results. That is that over pure zinc oxide, we have a catalyst which is rather active, but very poorly selective for making C2 products. And one of the reasons that that occurs is because zinc oxide reacts very efficiently with the methyl radicals. But if we put only a small percent of lithium on the zinc oxide, then we greatly modify this reaction of the methyl radicals with the zinc oxide, and thus allow the methyl radicals the opportunity to combine and form the C2 products, and those C2 products can then escape the catalyst bed. Go to the next slide, please. I think, let's go on to the next slide. And the next one. Well, I hope that I have given you a brief overview of some of the roles which these surface-generated gas-phase radicals can have in heterogeneous catalysis. You'll note that all of the examples that I've chosen are cases where we've been involved in oxidation reactions. And in particular, the case of the oxidative dimerization of methane, we've been talking about high temperatures around 700 degrees C. And it seems to me that these are ideal situations for the generation of these radicals in sufficient quantities that they can be involved directly in coupling reactions. Of course, there are many other ways that the radicals can be involved, for example, in initiating chain branching reactions and so forth. And I've just illustrated one case where they can be involved in coupling reactions, but it happens to be an important case. And finally, I would like to acknowledge the people who have been involved very intimately in this work and have been very successful in putting the system together and maintaining it. Wilson Martyr was a graduate student, was involved in actually building the system. Dan Driscoll and Ken Campbell have been very helpful in my laboratory. They've since gone on, graduated, and had jobs. Yudong Kong is currently in my laboratory and is doing the work on the reactions of methyl radicals with various oxides. And Mr. Wong and Mr. Song have been very helpful in preparing catalysts for us. And also, I'm indebted to the Office of Basic Energy Sciences and Department of Energy for the financial support